$15,000 setup or the $100,000 setup, but there will also be the $10 chip that's running in your notebook. It will be, in every corner of the market out there. The only thing it's not explicitly going to be in is your cell phone, because that's ultimately different sort of everything on one chip sort of deal like Tegra. So yeah.
Also, you mentioned like the PCIe bus is this huge bottleneck for all that. But you can do a lot of real-time stuff like real-time ray tracing because everything just needs to stay on a video card. But what about having these really big servers that have lots of that don't need to have their results go out to video? Like, what if they need to send it out on the network? Is it going to limit real-time capabilities for things that do need to go back to the CPU?
Well, so first of all, going out on the network, if you're talking about massive sets of machines all sharing the data, obviously the network's really going to be your bottleneck. I mean, it doesn't matter if you've got InfiniBand or MirrorNet or whatever the fast thing today is, that's still going to be your bottleneck because it's not going to be as fast as what's inside. That having been said, your problem is really just how to appropriately chunk. You can still compute on the GPU far faster than you can on the CPU or on this distributed network. You just have to be intelligent about how to chunk and batch. I don't know, that might not answer your question, but.
Yeah, I'm just wondering, because it doesn't seem like you're ever going to get past this bottleneck with the PCIe bus, like you make the card faster, but you can't really solve that problem. Is that going to always kind of prevent real-time, non-graphics, applications from being run on the GPU?
Well, so I would say it's not actually preventing real-time non-graphics things from being run today. A lot of the supercomputing, well, I don't know if you can call supercomputing real-time, but I mean, when you're talking about large distributed systems like that, I guess the best answer I have is to say that it's not actually holding things back today. It's just really, it's informing the way people develop. It is a hard limitation, you're right. You'll never be able to get that interconnect between machines as fast as you can between whatever's on a chip or between whatever's on a card. And so it's just, it is now and probably always will be a limiting factor. Even if you had massive fiber connections between everything and you had a 40 terabit connection between each card, you still have latency issues because speed of light between here and here, speed of light doesn't matter much over 1 centimeter. Doesn't matter that much over 9 centimeters. 9 centimeters starts to be a problem. 30 centimeters, longer distances, speed of light becomes a big issue for latency. And so then you start being dragged down by latency issues. And you start dealing with that by scheduling throughput with chunking and blocking and everything else like that. But it'll always be a consideration. It'll never go away. It just changes algorithms.
I was wondering if that was an existing problem that kind of wasn't talked about, or if it actually is something that people.
It's definitely a problem. It's not something that's faced by games, obviously, really.
Yeah.
But supercomputing, that's a big deal. As much as the supercomputing guys might spend money on our hardware, they spend probably just as much money on network interconnects and the supercomputer. I mentioned InfiniBand and MirrorNet and stuff like that. That's all old school. I mean, that's like 2003, 2004. I haven't kept up with what they use now, but I'm sure it's faster. I'm sure it's probably these days fiber-based, and they are pouring a lot of money into it.
So I don't know if you've heard of the people who are trying to stream games over the internet.
Oh, yeah.
But is that, I know Adobe's doing the same thing with Photoshop, trying to get Photoshop online and all that. Is that using, they're using custom video hardware? They have to be doing something.
I have no idea. I actually find that fascinating. I would have said before I saw so much glowing praise for it, impossible. Just because, getting compressed video over the internet, sure, all right, but yeah, internet's fast, you can do it, but I would have thought that the latency would have killed you. But somehow you can do it. So I would expect that underneath they're using lots and lots of rendering hardware. I wouldn't be surprised if they have some gnarly farm that they're planning, but I don't know any details.
I saw that Microsoft's Direct Compute, they advertised that one of their roles for their compute shaders is that you can do post-processing effects on the frame buffer. So is that something that CUDA can also do? I mean, it seems like that if DirectX could do it, that CUDA should also be able to.
Yeah, absolutely. You can do it. It requires CUDA and OpenGL interop. I don't believe, although I could be wrong, that CUDA and Direct Anything cooperate. It's possible. I'm just really not from that side of the house, so I'm a little ignorant. Any other questions? Yeah.
One sort of about, not less about this, but about your guys' driver. I do a lot of graphics programming just generally, but I generally just see sort of the OpenGL calls and the shader and the pixel shader and ultimately the frame buffer. You sort of hinted at there's more stuff that you guys sort of do in the background. Could you elaborate sort of on what you guys do that doesn't get seen from?
Yeah, all right.
You know?
So, so let me sketch out really quick what from the driver point of view, what the GPU looks like. Calling this CPU, but really this is just non-GPU space over here. So we've got your app. By the way, I type all day, every day, and my handwriting is really deteriorated, so,
Your future.
Yeah. So the app, obviously, we've got the driver, and we'll call it client, kernel, and then over here, so there's a lot more to it than this, but this is like a really high look at it. The front end that we talk with the most and the high level, so there's different parts of the driver. There's at the kind of the high level there's OpenGL or CUDA or whatever. At the lower level underneath that there's something called ResMan or Resource Manager, and they handle a lot of low level details about like programming registers on the GPU and things like that. But for us at the high level part of the driver, we primarily talk with host. Host is the front end to the GPU, and what we do is we send command buffers, streams of commands to host, and host is responsible for parsing through that stream of commands and distributing it on as it needs to go throughout the GPU. So we actually have channels that communicate, and in the Mac case, the channels actually go from the kernel to host, and so the app will call a whole bunch of GL commands. And at the client level, we take, for example, we take your shader and we compile it down to machine level instructions. And we do a lot of optimizations on the compiler. And in some cases, we know that some really popular game has this shader that we can actually make run twice as fast if we substitute our own shader that does the same thing in. So we'll say, oh yeah, this is so-and-so's shader, chuck it, put it on our own version, and now we compile that and stick it in. It does the same thing, but runs twice as fast. We also set up all the other state that the GPU needs. VBOs, you program these vertex buffer objects. So what we have to do is we actually have to allocate space in the frame buffer. We might have to allocate some space in sysmem. Sorry about that. And then we have to let the GPU know about this allocated space, because in one sense, allocated